So part of the interest in the CMB is because it is the oldest light in the universe. That means anything that we interact with, or anything that's interact with light that you'd ever want to see or could see, you can't see that event before the formation of the CMB. The universe was a pure plasma, and in plasma, light doesn't propagate freely; it gets scattered. It's like the sun is a plasma. You can't see into the sun; there's too much scattering. But if in the early universe, all we had was protons, neutrons that were bound with other protons, and electrons and heat, until the universe expanded enough and cooled enough that you could see from the last scattering event that ever occurred for those photons to today. So that light came straight to, that's what this globe is. It's a picture, as God would see it outside of our universe, of what the different temperatures of photons would be as they were at the surface, when the surface was comprised of dark matter, ordinary matter, and photons. We see that light, it comes to us. It tells us about all the events that occurred before then. So it's the longest leverage that you could ever have on phenomena that involve light or propagate at the speed of light. Gravitational waves also propagate at the speed of light, as you know. And they do imprint the CMB with a specific type of pattern that we are hoping to see. But not only that, any type of matter will interact, and just as that glare showed us before, when light interacts with matter, it develops polarization. It's called Thomson scattering. Thomson scattering can either tell you about the properties of the light or the properties of the matter. But if you know the properties of light, which we know very accurately is a black body, then the polarization tells us about the quantity or composition of the matter. So we can kind of reveal how much of that matter could be dark matter versus ordinary matter. And there are other more sophisticated ways to do that and to see that there could be a coupling that are highly speculative. We have no idea if this is true. We know for a fact that dark matter exists. We see it on every scale outside of the solar system. We see it in our galaxy, clusters of galaxies at the CMB, baryon acoustic oscillations. We see every single example of a gravitationally bound structure has dark matter, but we don't know what it is, so it's frustrating.
So in your book, you mentioned a lot about the stardust, or like in general, like maybe some nanoclusters are flying around, or something which it's difficult to see from the Earth. So could it be dark matter, something else what we're looking at? Or?
No, it can't be dark matter. So if you pick up that meteorite there in front of you is a giant chunk of dust. So the dust that kind of obscured our view of the CMB was ordinary matter in our galaxy. Dark matter doesn't interact with light. This matter does interact with light. So what happened with this matter, these tiny grains of micrometeorites basically from a detonated supernova that blew up 4 or 5 billion years ago in our galaxy, not in our solar system, in our galaxy, that made little particles basically of iron filings, like a compass needle. The galaxy has a magnetic field that then aligned those particles along a preferential direction, which made exactly the same type of pattern that the CMB would produce if gravitational waves are present. The only way to get rid of that is to go beyond the galaxy into intergalactic space, which is very expensive and difficult to do in these funding climate time that we live in. But it's ordinary matter. It's matter that interacts with light. So dark matter, its key characteristic is that it does not, you should really call it invisible matter. It's matter to which light is impervious to, kind of goes right through it. And there are examples of dark matter that are familiar to you. They're called neutrinos. Neutrinos do not interact with light. They go through ordinary matter, light years of ordinary matter without any chance of scattering, and they have mass. Neutrinos are known to have mass. So they have all the characteristics. The problem is they don't have enough mass, and there aren't enough of them to make up the preponderance of dark matter that we see through all these cosmological surveys and that we know exists, but we don't know exactly what it is. So people have proposed these other things, as you said, Shungwei, called axion-like particles, or ALPs. And these are particles that are kind of like heavy photons. And they reveal themselves in that they will cause the polarization state of the CMB to behave slightly differently than it would if they don't exist. And you can measure the product of their cross-section and their mass the same way a dark matter experiment would do them effectively. The more the mass that they have, they'll affect the dark matter. The clumping of dark matter will be affected the more massive they are on smaller scales. So you'll have more clumping at small scales, less clumping at large scales if they're heavy, and then the converse is true if they're light. These are very light particles. These are like 10 to the minus 27 electron volts or something. I mean, incomprehensibly massless, but there's so many of them, like there's so many photons that they could comprise the dark matter that we do perceive indirectly.
And can you reevaluate data from older observations to evaluate this, or do you need to build new, more sensitive or at different frequencies?
It's kind of like, could you take a picture, could you make an Apple Vision Pro, with a camera, from 1999? You could, maybe. It wouldn't be that good, and it certainly wouldn't have all the features and the resolution and the quality of it. And so one or two, because the field moves so fast and people can build detectors, and we kind of are outpacing Moore's law in terms of the number of detectors, the sensitivity of the detectors, it just doesn't make sense to do that. Like in 1 year of data with the Simons Observatory, we can do everything that BICEP did, in 3 to 6 years of observations, and way more. I mean, we could do a lot more than that. And so it doesn't pay, although we are analyzing data from experiments that we've decommissioned at the same site in Chile, but different purposes. Also looking at polarization, but it wasn't originally designed to look for dark matter masses.